used this. I have differentiated. I've used these two terms in commonly here, power and energy. Basically, there is a difference between power and energy, right? So power is basically the instantaneous spurt of energy, right? At that particular moment, that is what we call it as power. While energy is throughout the period, right? Say for example, the vehicle has started its journey and then it takes a drive of 20 minutes. So how much energy that has to be consumed within these 20 minutes? That is something I need to figure out. While power is at that particular instant of time. For example, I accelerated. So what I want is basically a power. So power, the time t is not much relevant in case of power, but t is very much relevant. Time, the t, right? T is very much relevant in case of energy. But then the issue here is we want to properly utilize the onboard stored energies. What we mean by that is there is a generator, there is a battery, then there is an electric motor, and there is engine, right? And then there is this braking, regenerative braking. So power or energy is flowing across, right? So what I want to do is I want to design a high level control algorithm that ensures proper power flow between the vehicle powertrain, the generator, the motor, and the battery. For what reasons? Because I want to optimize the system energy flow. I want to minimize the emissions. I want to estimate how much of energy is remaining and how much of driving range that I could obtain from my vehicle. I want to maximize the regenerative braking energy as much as possible because it helps me charging my battery, right? And to prioritize real-time power requests from the vehicle auxiliary electric loads. So auxiliary electric loads means, for example, along with my traction requirements, there are some auxiliary power requirements as well. For example, I would be using headlights, I would be using tail lights, I would be using infotainment system, I would be using wipers, right? So all these loads, power loads also needs to be taken into consideration. These have to be addressed. And then to efficiently allocate the power from energy sources. Because I may take power from engine, I may take power from battery, right? I may run engine, I may run motor. I may use generator to charge my battery, or I may use regenerative braking to charge the battery. So what I want to do is I want to manage the power flow. I want to manage the energy flow, and that is what this issue is all about, right? So basically it has two parts. One is to divide the available power between loads, and the second is to be able to integrate and arbitrate multiple energy storage system. However, this is very important line when we say there is currently no consensus among researchers and the industry as to the best way of addressing the power and energy management problem. So point is, as a hybrid vehicle manufacturer, you want to regulate, you want to manage the power or energy, but how do you do it? There is no as such one common rule, right? So you can have your own strategy, and that is what is at the heart of devising the control strategy, designing the control strategy, right? So managing the power and energy of a hybrid energy storage system poses many challenges. Why? Why it is a very challenging issue? Because there are differences in the physical, electrical, and chemical characteristics result in different. So because the electrical, chemical, and physical characteristics of, say, for example, battery, electric motor, engine, generator, right, or that motor, right, motor, or which works as a regenerative brake. So there lies a difference, right, and that's why this issue becomes very challenging, right? So it results in different power, energy, voltage characteristics, and charge discharge methods. So due to these differences, the interaction between these systems require careful study and verification. So this is very important issue, power and energy management of HEVs, and that is where most of the hybrid electric vehicles or papers are being published. There is a lot of research that is going on in this area of power energy management issues of hybrid electric vehicles. So we can have, of course, multiple strategies or techniques to address this problem. For example, we can have optimization based way of doing it, or we can have a rule based strategy that we may use. In case of optimization, we can have global optimization. We can treat it as a real-time optimization problem, right? In case of rule-based, we can have deterministic kind of thing, right? Or we can go for fuzzy logic kind of strategy, right? So the choice is with the developer, the designer, the researcher, right? So every company, every manufacturer, every startup will have to deal with this issue of power and energy management issue. Okay, I think we are coming towards the end. We have got around 20 minutes remaining. So maybe in the next 5 to 10 minutes, I will talk about this optimization based control strategy. And then I will summarize, and then for maybe last 10 minutes, we will see if we have got any questions from the participants, right? So we will see number of papers coming up on this optimization based control strategy. So basically what we do is we treat this as an optimization problem, right? And typically when we talk of optimization problem, we talk of uh, function, right? So what the idea here is, we want to minimize the vehicle emission and fuel consumption, right? While considering the torque demand and component and energy limitations. So point is, we will have to devise the multi-objective cost function. At the heart of optimization problem is devising the formulation, that is the multi-objective cost function, along with constraints, right? So what is the idea here? What we want to do? We want to reduce the emissions. We want to reduce the fuel consumption. At the same time, we want to ensure that the adequate torque always made available to the driver, power and torque, right? And then all the components are used at their optimal level. And then there are, of course, multiple parameters that come in the picture. So that's why sensitivity analysis becomes very important. So resulting in sensitivity to system parameter variation, system uncertainties, imprecise measurement, and noises. So what it means is, so there are a number of parameters which are influencing this particular behavior, power management issue. So if I make a change in one parameter, then what kind of effect that one can expect, one can have on the outcome, right? So this is what is sensitivity. And then I need to have constraints as well. When I talk of optimization problems, I need to take into consideration the constraints. So what kind of constraints I may have? For example, I would be either minimizing or maximizing the objective function. So I want to consider some specific set of constraints, right? So these could be what kind of constraints? For example, dynamic resource allocation, or physical constraints of vehicle components, or uninterruptible power availability, or there are power quality issues, system stability, fault diagnosis and prognosis. So all these constraints, or out of these few, I may choose the more relevant constraints, right? And based on that, I can uh, solve the optimization problem, right? So this is something which has got to do with the optimization problem solution when someone works, or someone considers it as a research problem. So what I want to optimize, I want to optimize the uh, performance of hybrid electric vehicle in terms of power and energy management, right? So what I want to do is, I want to lower the emission levels and fuel consumption, but it should not come at the cost of power and torque. I want to ensure that the adequate amount of power and torque is made available to the driver, right? And then all the components are utilized to their best efficiency levels. And then there are some constraints as well, as has been mentioned here in the last part of this slide. So these could be dynamic resource allocation, or physical constraints, or uninterruptible power availability, and so on, that just we have talked about, right? So dynamic resource allocation means what? As we have said, the power requirement is not going to be same, right? So there could be peak power requirement. There are some certain moments where the peak power requirement is desired, while for most of the time levels, your power and torque requirement won't be at the peak, right? So it's just impracticable to design the vehicle's power system to meet the peak power demand for all loads. This issue one needs to take into consideration. Or then there are going to be some physical constraints of vehicle components. For example, batteries are sensitive to temperature, right? Or they have limited lifespan. Say, for example, 500 cycles, 1,000 cycles, likewise. Or they have limited capacity for power and energy, right? So this is what we mean by physical constraints. Or uninterruptible power availability. Why? Because there are certain systems wherein you simply cannot compromise with regard to power availability. For example, steer by wire or brake by wire, right? Or safety restraint subsystems or some military systems, right? So these are very sensitive systems where you want to ensure uninterruptible power supply. So this is again going to be a constraint, and maybe you will have to use one or more backup batteries in that case, right? But the point is that such issues have to be considered when we work on this optimization problem. Power quality, this is again very important because the power quality issue is very important because there could be sudden voltage drops or voltage spikes, right? Owing to the temperature change or owing to the sudden loads, right? And that's why this issue also is very important and needs to be taken into consideration. Sometimes system stability becomes a very important issue, or there is some requirement of fault diagnosis and prognosis, because with lot of electronics there is a chance that something will go wrong. So ideally you would like to enable your system to be able to do the fault diagnosis, right? And then prognosis as well. Or in a more sophisticated system, you would like to use something like artificial intelligence, and in that case your system itself should be able to give you some kind of warning that says some system or some subsystem or a component may develop a fault and you need to address it, right? So these are some sets of constraints that one will have to take into consideration while